Roland Bacon. He's a pioneer in things that we are going to hear. And you will see it's an enormous work and contribution to astrophysics. Professor Roland Bacon is an emeritus researcher at the Lyon Center for Astrophysical Research at the Observatoire de Lyon, where he was director for 10 years from 1995 to 2005. Between 2014 and 2019, he held an advanced grant from the European Research Council. His research was focused mainly on instrumentation for Large Optical Telescope and extragalactic astronomy, allowed him to lead mainly and participate in more than 350 publications. He's the author of the monograph on 3D instrumentation called Optical 3D Spectroscopy for Astronomy that he wrote in collaboration with Guy Monnet in 2017, published that year. In 1987 already, he realized with Georges Courtès and Guy Monnet the first integral field spectrograph in the world, named TIGER, that comes from Traitement intégral des galaxies par l'étude de leurs raies. In English, integral processing of galaxies by the study of their lines. But it's much more fun with TIGER. He has since led many instrumental projects for optical telescopes, including the Sauron integral field spectrograph, which has produced a series of publications on nearby galaxies. He led this project together with Tim Desu and Roger Davis. In 2001, he designed and led somewhat that I'm sure you all know, the multi-unit spectroscopic explorer MUSE for the VLT in Chile, which is there in one of the VLTs in Chile since 2014. He was a member of the Scientific Council of the Permanent Exhibition dedicated to the question of origins of the Musée des Confluences between 2006 and 2013. And he also directed with the dance company Allais et Gaillan, a show on the origin of the universe with a very interesting title, Trésors et des poussières. So a little bit more than half a day, I guess. This show was produced 20 times between 2009 and 2016, mainly in France, but also in Switzerland, in Morocco, and in Algeria. Amongst the honors and awards he has received, he's got the 2013 award from the English Royal Astronomical Society with the whole team of the Sauron project. In 2017, the Delandre Prize from the French Academy of Science. In 2018, the Man Sigman Medal from the Nobel Foundation. In 2020, the Jackson Guild Medal of the Royal Astronomical Society, that is awarded for outstanding invention, improvement, or development of astronomical or geophysical instrumentation or techniques. In 2022, the prize from the Johann Wehm Foundation in the Leibniz Institute for Astrophysics in Potsdam. And in 2024, the prestigious Ludwig Volter Lecture from the European Astronomical Society. Today we have him here with us. He has been kindly to accept our invitation to come here, and he's going to talk to a new project, the Wide Field Spectroscopic Telescope. Thank you very much, Professor Roland Bacon, for being here.
Thank you very much. Looks like it has been a long time. No, it's really a pleasure to be here, and for some unexpected reason, it's my first visit, so I think now I'm really pleased to be there. I'd like to thank Pepe for inviting me and all the directors and the staff. So it's a great pleasure to be here. And, you see, so when you have such a long career, I think what you can do at the end is to transmit. Of course, this is all what we have to do, and I think it's very important because we know that science is built by doing things over time. I think not trying to reinvent everything, but to progress. And so for very long time projects like WST is, clearly it's not something that I will do for myself. But I think this is very important that we can really use what we've learned over years, how to do things, because how to maybe some sort of vision we can share, and then all together, including the younger people, I'd say, make it happen and make science of it. So I think it's really the heart of what we should be doing. So, okay, so that's, I think, this is, I'm speaking about, on behalf of the very big WST consortium. We'll see in a moment. I'm going to give a broad overview of the project, focusing more on the science and a bit on some technological aspects. And as I said, I will be here this afternoon as well tomorrow if people want to discuss further things. So really, this is the purpose of my visit. Okay, so is it moving? No. Okay. So WST is really the basic idea is to have a facility, innovative, to answer really a wide range of questions. See? So you can arrange things by topic and so on, but you see on all scales, because I think astrophysics is by essence a multi-scale science, where if you want to understand, including things that at the bigger scale like cosmology, you have also to understand the micro scale. That's all what is make astrophysics interesting and a bit difficult. But I think having something multi-scale is very important because then you can handle the various phenomena that play all together to try to answer the big question. So it will cover most of the scale from really the nearby planetary to the universe itself. So having a facility that could do really big spectroscopic survey, which a large telescope has been floating in the air since a long time. And in fact, it has been part of most of the community projects. And it's, for example, it's on the roadmap on the Astronet European Vision, as is one of the top priority that was foreseen to be important. And the reason why is that because you will, I think, hopefully will be convinced that, of course, spectroscopy is what we need. Imaging is great, can do a lot of things with imaging, but if you want to qualify the object, to understand the physics and so on, you need to go to spectroscopy. And then, of course, we have many instruments to do spectroscopy, but to go to the next scale, because the imaging now is going on, we have Vera Rubin produce billion of images. We have Euclid and so on, Oscar and so on, Roland and so on. So for images, I think we're set. You can probably point any point on the sky in a few years. You will get HST like resolution and maybe multi-band imaging. So you can do a lot of things. But what will be the bottleneck is the spectroscopy. And this is what WST is aimed for. So, as you know, the big things, which is ELT, is coming. It's really already quite impressive if you go in parallel to see these huge things. So it will be fantastic things, but see, it's not yet there, but we still have to think about the next step because for doing such big facility, it takes 20 years at minimum. So from the ELT first idea to the expected first life would be 30 years. SKAO was probably almost on the same scale. So this big facility now takes 20, 30 years. So we cannot just do them in a row. You have to advance in parallel the thinking, what you want to do. And this is critical because if you do this instrument, this big facility, rather than any other, it will really, it's something which you measure for the European community. if you do that, you won't do something else. These choices are critical for the science, for the prospect we want to make. So I think, and then ISO has some difficulty, of course, to go into the ELT, as you know, because it's a very big thing, very difficult, very costly, and so on. But it's very well advanced compared to the other competing projects. So that's very good for us. And so they have decided now to open a process to select what will be the next one. And this process is called expanding horizon, which will be what will be next. And they set up as a sort of timeline 2040. So it seems a long way, but not so long way. It's 15 years. 2040 plus. So you see, given the timeline, we are ready to think about what we'll do and in order to be prepared to exploit the science at that time. Okay. And the process is open. If you have an idea, you can propose it, of course. So the idea is to put WST as the next big step. So it's not guaranteed yet. Okay. But how we get there and how we try to think about the science and the technology, what would be best for the community. I think WST, I think, is one of the front runners because he can really bring new science and also with some technologies that we can do, but going really to the next step. So we have a big consortium. This consortium was based upon the people we know when we answer the call for the European infrastructure call. And so we get there, you can see it. And I'm here to correct a big mistake, is to put some color on this map. Because it must be an European project. I cannot see that all, say, important institutes that have some knowledge and so on should, in a way or the other, should be part of it. And that's, I think, the idea, how we can get there and get more of the experience, because it's a huge project. So here's the requirement we have set after a number of iterations. Of course, you know how it is. You derive science case. On the other case, you look to what is possible to do, impossible to do, maybe in the near future, but still feasible. You see, this sort of trade-off always difficult to get advanced, but not to dream too much. But we have to dream still. And we get to this, I think, a very strong requirement. So we come for a telescope aperture of 12 meters. Seeing limited, at least mostly for the MOS. For the FS, we probably will use GLO with a huge field of view. So that's 3.1 square degree. For such a big telescope, you see it's really huge. And with a spectral range coming from the visible up to the infrared. And it's a facility. So there's only 2 instruments, but significantly big instrument. In fact, the instrument will have a larger part in the cost and so on than the telescope itself. So we built a telescope around the instrument. You will see in a moment. So the 2 instruments is the MOS and the ANS. The MOS has 2 modes, a low resolution mode with a huge multiplex. 30,000. So we are today proud that we are putting foremost on the sky with 2,400 fibers. This is great, and we do great science. Oh. Now we put 30,000 fibers on a 12 meter. With a spectral resolution between 3,000 to 4,000, depending what, maybe a bit more in the red, and a spectral range that covers the full visible range simultaneously. Then we have a high resolution mode with a smaller multiplex because it will target much brighter targets, but a spectral resolution very high for such a big telescope, 40,000. And again, it covers in the visible, but only 3 to 4 regions to be decided, of course. Then the second instrument is an integral field spectrograph with 9.5 minutes square field of view. A spectral resolution of nearly 4,000 in the red, and the spectral range covers the full visible range. And you will see later, he has a patrol field that means it can be moved into this direction. The two important points, which are operational points, which have a strong impact on the design, is that the MOS and the FS do operate in parallel. I mean that whatever you do, you have the FS there and the MOS, and you have to decide who drives the telescope and so on. But this offers, I think, much more science for the same instrument. And we also have target of opportunity implemented at telescope and fiber level, because we foresee that time domain science in the 2040 will be really important, with all other facility will come online, like the Einstein telescope and so on. So it will bring really on from the start, to be sure. So it's really a big field of view. And you can see there that the MOS area with the 2-degree field of view, and this is compared to the VLT here, and to the ELT. So you see how big it is. And then in the center of this big field of view, there is 30 dark minutes, which are removed and which are sent to the FS field of view. And the FS field of view, so it can be placed anywhere into that area, and that's the EFS field of view. So in principle, for example, you can do a mosaic of to 9 by 9 arc square. And just to remember a comparison, this is a Muse field of view, which we are very proud. It's a very big field of view at that time. You see, so you see the change. And so you mentioned that you see that the telescope were going up to the infrared, but the first the first instrument are not going to infrared for a number of reasons. So we expect to have an upgrade plan, because such a facility, which more will cost at the end 1 billion probably, will be there for a long time, like the VLT, like the LT. So we should be able to expand it. So the idea is that few expansion we foresee is that an infrared upgrade for the most low resolution. Most mini FUs are being considered, and GLO system for the FS. That's maybe other. But so we looked at the design we have. Those do not preclude to have this extension in the longer term. Okay. So we can compare this to the existing or to the planned facility. So let's compare the MOS. So here you compare the MOS, you have the telescope aperture. So we go to the speed and to the depth, how faint the object you have, and the MOS multiplex. This is the classical metric to measure how the MOS can perform. And the area of the circle is proportional to the étendue, to the A omega, which also is related to sort of speed of the survey. Okay, so you see here the existing one. So for most waves that are coming in operation, DAISY already, PFS, okay, moons, then some planned one like Spec S5 in US, not yet decided, of course, it's just a plan. MUST, which is a 6-meter telescope in China, and WST. So you see two things that WST stands, of course, because of the high multiplex, the big aperture, of course, much better than the others. And also mention that's the LT instrument. Okay, so mosaic here, WFOs manifest for the TMT and GMT if they are ever built. And what you can see that the étendue, of course, it's a very big aperture, but the étendue is very small because it's very difficult to build large field instrument for a large telescope just because of the conservation of étendue. So there's nothing you can do. So reality will do very different and great science. But mosaic has a multiplex of 300 at most. Okay, nothing compared. So in fact, it's a very different science aspect and allow to do very different and complementary science to the LT. Not that. Now the EFS. So that EFS, that the monolithic EFS that have been built. So you have the muse, soon the blue muse, wave, a few small WST, and then the FS for the harmony for the LT. Again, big aperture, but very small rectangle. And you can see that WST stands completely unique. Okay, so how it looks like? I will be brief on that, but we should. So maybe I should be there because of the microphone. Okay, so that's how it looks the telescope. Not the design has been evolved, but not so much. So here, so you have the primary mirror, which is an F1 Cassegrain telescope with the primary and the secondary here. And the mirror is a 12 mirror, 12.4 meter size. That's a segmented. The idea is to use exactly the same segment than the LT. So of course, there have been huge developments and costs to develop this. So we're going to use the same. Of course, the optical prescription will be the same. All the tools to handle them and so on will be similar. Okay. And then why 12 meters? Why not 14 or less? Because we use this segmented mirror, I think it's quantified. So if you do one less, you go to 10 meters. And as we see, 10 meters maybe not really enough, if you can do better. And then the next step would be 14 meters, and then it's very difficult for the instrument. So if you want to maintain the field of view, I think it's the very big field of view, high-multiplex and so on, is probably the sweet spot that it's 12 meters. Okay, then the light goes there, goes to the secondary, which do all the tilt and so on that is needed. And there is the sunlight from the MOS and EFS beam, so both the light of the telescope, and you have the field corrector and the atmospheric dispersion corrector, which is there. Very big lens, the biggest I think we can today use safely, which 1.6 meter, I think. And then they go there and they are sent to the MOS focus positioner as the correct ratio for the fiber spectrograph. We go to F3 here. And then in the center here, what you see that the light is sent back to a set of mirrors to the FF. So that's where we extract the 13 arc-minute patrol field from the FS, which is then sent to the Lasvis platform relay, where it's sent back to the EFS station. So where are the instruments? So all the MOS instruments, the very big high resolution and the numerous MOS one are into the azimuth platform. That's to limit the size of the fiber, especially important with the blue for the throughput. Okay. And the FS, which is a huge number of spectra you will see, is sent to the Coude focus, where it's stable, and we have the derotator thing, and so the idea we have all this huge number of spectrographs there. So there is some innovation, just to mention a few, of course. So innovation in terms of the telescope, which I already mentioned, is the big field and the large aperture, which transfer to étendue. So WST will be the largest ground-based telescope in terms of étendue ever made, even bigger than the Rubin and SST. Okay, much bigger than the Subaru, of course, usually bigger than Mosaic and the VLT. The second is what I mentioned. It will be the first ground-based telescope, big ground-based, to do multiple focal plane at the same time. Okay, it's usually done on space instruments, but not so much done on ground-based. It has a huge advantage here. it came with some complexity in terms of the operation scheme and how to do the wavefront sensing. But now we have finalized the design. We have a very good design to do that. Second is instrument, of course. So then the MOS positioner. The MOS positioner, 30,000 is quite challenging, okay? Because it's not like, so the focal plane is somewhat big, but somewhat limited. So it must be extremely small pitch, I think a few millimeter, and density of the fiber. So we're looking to various positions. In fact, we have 4 concepts we are looking in parallel. So there is a tilting spine, which is the one which is used in foremost, the classical. So it needs to be drawn much smaller and much denser than it is down. There is a very new design was proposed by Roland at AAP, which is called a flex design, which is inherited from a surgery system that is used to do something in the eye, and that will allow to do this extremely dense population of fibers and still keeping the focal plane at the same position. The curvature sometimes is a problem. Second one is the theta phi positioner, which is really well developed by EPFL. And there is a R theta flexible positioner, which is studied at UKT. So we have 4 designs. We are going to select what we think is the best one soon. Then spectrograph. So the first thing is we have many spectrographs and many detectors. So for the FS, we have an optical design. We go to 192 spectrograph, 2 arms. The most low resolution is a bit less, but 3 arms. The most high resolution, very few spectrographs, only 7, but they are huge. They are cubic meter optics. And so if you get the total of this, for example, so the number of detector, and we are probably moving to CMOS for a number of reasons, will be nearly 500 detectors. And the data produced is 23 by 8 gigapixel for each exposure. That's 7 times more than the Ruby. So it's really big data. So spectral design, I think it will be a major cost for the facility. So we have developed a system that can maybe simplify very much the design. It uses a curve detector, which are being developed by various people, including in lab. And you can see a curve detector. It's really simplified the design because you can remove the curvature rather than trying to flatten it with optics. You do on the detector itself. For the MOS LR, we have with Sodos, which provide an interesting design with a folded Schmidt camera, which were used in the past, but which are the advantage to be extremely fast. You can go f1, even f0.8 camera with a good image quality, and still have the detector outside, because having the detector inside is a problem. So that's we're looking to all that. Not yet down to what will be the final design we select, but I think it's moving forward. So where this facility will be, it will be in Paranal. Paranal is the best site we know, and there's a number of reasons to do in Paranal. So there is a various peak still available. So La Montura, La Quira, Maquena, Ventarnes. So this one are within the Paranal, Amazones, ESO concession limit. So La Quira is your preferred site because we don't have to negotiate with Chile to get access to these 2 other peaks. And it's further still away from VLT, LT, not to be touched by all the laser collision, because we operate in the visible where all the laser, there will be a lot of laser. They are already in VLT and VLT as well, so it's good. Incidentally, it's also far away from the bad new industry that's planned to put something there. Hopefully they will not, but in case we are in the safe direction. The other point to put it in parallel is for sustainability. You don't no need to develop a new site if it's good. Energy will be something you need to look with a lot of attention. It's part of the trade-off metric that we're looking for the development. The reason for us to move to CMOS is that we can cool them to lower temperature and power consumption is much lower. All that. It's also that solar parallel solar plants that will provide green energy to the facility. So I think that's also something we need to take into account in 2040. We cannot build facility that we've done in the past. Of course, this is something very important we have to do. So, with such a facility, in just 5 years, this is an example of operation, we will provide, Mosalia will give access to 300 million of galaxies down to faint magnitude over the full accessible sky in the south, and 25 million of stars down to faint magnitude over the entire galaxy and the entire group. The high resolution with a few million to be defined yet exactly, but to brighter star, but of course much higher spectral resolution over most of the galaxy. And the FS, we provide 4 billion spectra over 30 square degree in various environments like low density field, galaxy, and star cluster. So what we do that? A lot of science. And a lot of science we are developing, and we expect you already participate, that if more can provide ideas and so on, how we can best use this facility, but we have, of course, already a number of ideas. So we have split in a traditional way the study of the science case into these various galactic, basal stellar population, extragalactic, cosmology, and time domain. And we already have a paper here, which is a white paper, first version. And we are going to release a new version, quite much improved. Already give you an idea of the vast number of things that can be done with such a facility. And most of the science is interesting, use either one, but usually a combination of these. Okay. So we have often the EFS looking in the center and the most low resolution at the same time, giving the outskirts or giving the relation with what you're looking with the environment and so on. So I think people have found a clever way to use this facility to be very efficient. The other point is synergy. That's something I mentioned. I think WST is one of the new facilities we have with very strong synergy, because this is what was important. I will show in the Flamberg with that synergy, of course, with the LT can provide interesting source to be studied with the LT, but with Gaia, Robin, and SST, very obvious. Euclid, Roland, SKA, or you will see there's quite a lot. Athena, the Einstein telescope, LISA, and probably many others. Because most of these facilities will sometimes need spectroscopy to really do their own science. So I go briefly, I cannot go to the very university of the science case. It's not all my science as well, so I'm less familiar, but I try to answer if you have questions. But so in the galactic science case, the main science theme we foresee are the origin of elements, the origin of the Milky Way system, in situ study of the Milky Way disk and bulge, and the origin of stars and planets. Okay, and that's the idea to build upon what we are learning and we have learned with Gaia, Phomos, moons, and WIMP. So one example is the origin element. So this is based on the most high resolution. So having 40,000 resolution give you access to a number of key elements that you can probe, diverse nucleosynthetic channel. And you can go also fainter. So you can study not only the really nearby stars, but you can probe up to maybe possibly the halo to study that. And that's offer a lot of science. They show, for example, how moving from just 20,000 to 40,000 offer much more access to various elements. So from that, for example is to study the neutron capture elements to understand a bit of the process, and the type 1 supernovae. The origin of the Milky Way, I think here is to get detailed abundance of the chemical arrangement history of the population structure in a way to track what happens into the various elements that you can really recover them from having access to the chemical abundance. So that's, I think, very important. And you see that currently what's expected to do with Foremost, if you study, say, on the red, I think it's there, we really do the nearby environment of what we can do. And then when we expand much further with WST because of the bigger aperture. And then we can even go, if you want, much access to everything if we can go to the red current stars. So there will be a full world-class survey for the high resolution and the low resolution, getting the full chemical information, element evidence, and the metallicity and radiabilities. In terms of resolved stellar population, let's go a step further. I think but you can still resolve stars, and I think this is something where, for example, a lot has been done with news, for example. And here, a lot of things can be done because of the much larger field of view and also the larger aperture then. And you can also connect what you're doing in the center of this much denser region to the outskirts. And so the idea is to use the FS to select the galaxy, the large galaxy we want to study in the local group, and use the most LR on the outskirts. So baryonic and dark matter are the properties studying the local group of dwarf galaxies and doing extragalactic archaeology, so abundance pattern in dwarf, in spiral arms, and the role of ultra-faint dwarf in galaxy evolution, also a way to dark the dark matter impacts, and also to study massive stars, which are very important, so progenitor of supernovae and so on, at very low metallicity. Now moving to the extra science case, it's a very rich science case. I know that you have contributed to some of it. So we have identified epoch of radiation, cosmic web, galaxy and their ecosystem, AGL, black hole demographic, and nearby galaxies. Probably doesn't cover all. So I give a few examples. So the epoch of reionization. So here you see that's a very strong complementary with SKA. So the SKA law will do a few very deep field, but at a low spatial resolution, I think it's 5 arc minutes. But then we'll be able to track the hydrogen neutral content up to very high redshift. Okay, and then if we have spectra and redshift and physical condition, including ionizing flux estimate from the galaxy, then you can specially correlate the spectra with the SKA tomography, right? And then get number of questions like the source of radiation, the scale of the organized bubble, doing that. So I think it's very important. SKA will be a huge development, and finally they will get significant size by the synergy with WST. The other item is to trace the cosmic web at big scale. So the idea here is to do very deep exposure, okay, using the FS and the MOS. And I think this is something which we just started with Muse, doing extremely long iteration to get up to the direct imaging of the cosmic web using using Lyman for 9. And we just showed that it works. It can be done. And so, of course, the first time we can really trace directly the cosmic web with facility. But with Muse, we've done these small things with 100 hours of exposure. So it's not going to extend to a size where we can really understand and probe the scale of the filament, correlate them with the galaxy population, what happens in terms of the environment, presence of the environment, and so on. So this is, we can extend to go to 35 megaparsec scale here, up from the redshift 2, because we start at redshift 2 with WST, up to redshift 5 or even more. So that's, I think, will open very new things. And at the same time, we'll be directly mapping the CGM of all the galaxies so we have learned a lot. And in the outer part, we will use the MOS and to use Lyman Break Galaxy as a tracer from the Lyman forest to get to reconstruct the filament structure, the cosmic web, but at lower scale, but much. So we can finally connect the very detailed scale in center to the lower scale. This is really, I think, something will be revolutionary to understand the impact of the environment with galaxy evolution. Another point is to reconstruct the dark matter distribution at redshift 1. And here, the idea is to use the MOS mostly and to do a complete survey, so complete in magnitude, to get very complete. And by getting very complete, you can probe the dark matter distribution because you measure distribution of galaxy, including at final scale, measure groups and so on, and then you get it. So this is what the impact foreseen. So this is the cone that was produced from the simulation, and this is one. I think it's probably a redshift 0.6 or something like that. One place where you can see the distribution. So this is the input. And this is what you will see with Foremost on DAISY. So you see a part of it, but you see you don't go faint enough to really get the full structure. Okay. If you get LSST, you go faint, that's for sure. But the fact that the photometric redshifts are not precise enough, especially to measure the group and so on, you get this fuzzy picture. And only WST will be able to reconstruct most of it. And of course, this happens really, you can test the lambda CDM paradigm, alternative dark matter model, the evolution of the halo mass function, the growth of cosmic voids, the emergency of the final planet. Again, huge science case and very important one. So we'll make a motion to that with Foremost. DAISY is trying to do that as well. But here, really, WST will bring the next step. On cosmology, there's a lot of things to do. Here I'll show an example on the massive cluster. So we know that we are going to have the knowledge of massive cluster will increase hugely thanks to Euclid. We discover a lot and so on, much more than we have now. And this, I think, is ideally to do with WST. So you can, So you can do the center of the massive cluster with WST, the EFS, and the EFS will ideally probe the central region of the cluster where you have strong dancing. Then you can infer from that the dark matter distribution with a very high accuracy. And then the idea is that to use the MOS to get an idea of the cosmic web structure and to understand how this massive cluster forms into the filament structure and how they evolve. So that's what we see. In cosmology, of course, they lack numbers. So the idea is that they will do a world-scale survey. And what's new, because a lot of things happening in cosmology today, especially with DAISY, which is probably new results, interesting one, which open even more questions in terms of the evolution of the universe. But here, I think the idea will push in redshift range up to 5 or even 7 with the IFS. And this is really new things because in most of what we do now with the 4-meter class telescope, we can only probe this lower range in redshift. So this is a sort of forecast they've done, how they can do here. So you see that WST is in red. So that's in redshift. So we can achieve fundamental parameter measurement at much higher redshift and much better than anything else. Okay, and that's opened a number of very interesting questions, like to constrain finally the level of non-Gaussianity, the sum of the total three inflationary model, test inflationary model, and modify gravity as well. So here, there's two examples of the neutrino mass. So here, this is the constraint that will be put by such a large survey. So this is what Planck can do. That is called a stage 5 plus Planck. But here, WST and Planck will really put constraint on the neutrino mass. Here, the primordial non-Gaussianity, which I think is important to test inflationary model. I think for the first time, WST will be able really to differentiate between multi-field inflation to single-field inflation. Okay. And time domain is not really a science case by itself, but we identify them because it has, of course, strong impact in terms of operation, and also something which I think in the long future will be coming very important, especially with LSST starting, but other things. So time domain can be, you can do foresee a lot of things, supermassive black hole, by looking to the evolution of the broadline region, compact object, stellar variability, of course, lots, and even solar system and comets, something that you have to catch up when they arrive. And so, just an example, I think in 2040, the LSST will have discovered hundreds of thousands of transients. So complete open really this field. And the fact that WST, in a way, could be seen as sort of spectroscopic LSST. Okay. This is the size and the multiplex you need to follow up this huge number of time domain events and you get spectroscopic information on it. Okay. So we'll implement as a fiber level TAO, where because we have a wide field, we can always put some fiber in a new thing that will be discovered. It's easy. And we will also look ourselves to spectroscopic variability, and I will mention that a bit later on. One example of time domain is the electromagnetic counterpart of gradient-Shorey events with the next generation detectors. Okay, so we know it's very new, so we've been able to identify only one for the moment. Okay, but the next generation will, especially the Einstein telescope, will discover thousands of gravitational wave events. And the thing is that you need to get spectroscopy to identify. So the things we do think about, probably optimal, is that when we have a great gravitational wave detection, even with the improved telescope like the Einstein telescope, it's still a larger area of the sky, but compatible with SST and WST. So in that case, LSST will probably find thousands of variable events at that time, and only spectroscopy can tell you which one is the correct one. And so this is sort of ideal of this, again, a very big facility that is going to be developed by Europe or by US, where such a big facility is required. And then I think, yeah, there is a few operation challenge. Right? Big challenge is the question here is how we can run simultaneous multiple surveys in parallel and still be very efficient with instruments that are very different, allowing time domain science, so to multiple visits and so on, and the ability to adapt to new science case in a reasonable time scale as well. So this is a challenge to being a survey facility that will also be able to adapt. How we can manage the data quantity and complexity with the need of rapid processing to issue alerts, and maintain homogeneous results across the survey and minimizing environmental impact. This is something we are facing. We look to that in Avenue, what needs to be done, and we think that here the community will have a big role because ISO is probably not prepared to do that by itself, and this is where probably we can play a big role. And we have experience in other big facilities like Euclid, Gaia, and so on. So we know how to work on that. We have new challenges. It's quite interesting. And finally, I just want to when you start to think about facility that will appear in the 2040s, you make the best to think about science case, and you realize maybe some of the very important science case was completely not foreseen. That's the life we have to face. But that will be true as well for the WST. So the idea is to see if a facility, what is the discovery power, independent of the science case we are building today. Okay? And WST has a really strong discovery power, which is different. So if we look to the MOSH, the discovery power is the power of numbers, which is, of course, very important, and a homogeneous data sample. So the SDSS, which has provided 10 million galaxies in 20 years, I think, has provided huge impact on astrophysics because of this big sample. Okay, so we can expect going from 10 million to 300 million, we will have the same. Huge impact can be seen as it's just a known example for people in extragalactic. It's called what's the galaxy deposition in mean star age versus stellar mass, and the segregation of population with the green valley and the red and the blue valley, which trace the evolution of what happened in the star formation history. And you can see that if you just take the SDSS itself, and you take just 1,000 galaxies, you cannot really see it just by going to the big number that you can see it. So this is this sort of thing that you can only see with big numbers. And there's a lot of things that happens in astrophysics doing that. Okay, stars as well. I think, of course, with 33 million stars in 5 years, there will be discoveries. In the FS, it's different, of course. In the MOSH, you do pre-selection. So here, it's just the number. But in the FS, there's no pre-selection. So the spectroscopy everything and observing all the time. You don't have to even select, do you do the FS and the MOSH? The FS will be always there. So the FS, for example, if you do anything galaxy, will be sit in the center. Even if you are not interested, it will do deep field if it's outside the galaxy, or study of what the galaxy, the star population needs. And it will go for free. And given the huge number of things, we can already say it will have a huge impact. So I'm really proud of this plot that shows the publication impact of news compared to the other instruments. So it's the most productive and the most demanded of instruments for the VLT. And part of the success is that while it has opened a new parameter space, but also that the data it produces is very rich. And some of the science you are looking for, or maybe will produce the science, but also other science. And people are using the archive also to use the data cube and to find new things. So I say we can expect, and comparing that, so the referring power is more or less the number of resolved voxel, which is the Sparksel plus spectral 1 in exposure. So in 5 years, this huge number will be produced. And if you compare, it's almost 50 times news, 90 times harmony, and much larger time than anything else. So yes, for sure, there will be a lot of discovery and unexpected discovery coming from the FS from it. And the final thing of discovery power is that the WST will be based as time domain machine. So it will be able to review something that changed in spectra. Okay, and spectroscopic time domain event is completely unexplored territory today. Okay, but so we know a few events that produce. So, for example, say a quasar that or the galaxies that have emission line that can change sometimes. But doing that systematically for all the 300 million of galaxies will produce also discovery of time domain. So I think it's also something new. Okay, so I'm almost done. Just show you the project timeline we have. So today we're here. So in blue we have the 3-year concept study that was funded by the Horizon European program. And so we are there. But the most important thing is the thing in yellow. This is the expanding horizon from the ISO, which will call at the end for a decision what will be the next facility. So we are there. There will be, we are already iterating. We'll produce a first set of possible science case. There will be the ISO call for either with a letter of intent, full proposal due by mid-27, then assessment by called a scientific senior committee and the ISO management, and with an approval expected by the end of 2020. Then a new program will be developed. If the ISO select WST, then we will really start to deploy and develop this program. The final things is that I think it's interesting to show how WST stands with what we've done in ISO in the past years. So if we look to the ISO flagship telescope, the main telescope that has to shape what ISO is doing. So we start with a 3.6 meter, which was the first light in 77. Then the big step was the VLT with the 4 VLT. The next big step is the LT, 29. You see, it's quite a number of years. Come back to what takes time to develop this. So if we look to what the development was in aperture, huge aperture gain, so this is completely foolish size of the 39 meter. If we want spatial resolution, I think that was really great. So from 1 arc-second, more or less, that was provided by EFOS. The VLT, thanks to the development of adaptive optics, go to 50 milliarc-second with the Muse down field mode. And the LT will go up to 5 milliarc-second with the Mikado. So huge gain in telescope size and spatial resolution. But in terms of field of view, of course, this has not been the same story because of the conservation of time. It's become more and more difficult. Coming from EFOS to the 3.6 to the 8 meter of the VLT, we still have been able to improve the field of view thanks to development of big detectors, development of new instrument facility. But it's not going to happen anymore because now I think that even with bigger telescope, the instrument becomes too big and so on. So with Mosaic, which has the biggest field of view using on Mosaic, will be only 7 arcings. So it will decrease. And the multiplex is the same. So for model 10, we go to 1,000 moons on the VLT, but back to 300. So what we propose is not to go to the same route, a sort of change of paradigm we want to propose to ISO, is to move really to still good aperture, 12 meter, of course, but huge field of view, huge multiplex, and good spatial resolution if we get to GL. So that's, I think, what we want. This will be a big challenge for ISO, not only for this change of goal, but also in the operation scheme, because we will be in the big data area if WST is done. And this is the end of my talk. If you are not registered to the science team, you are interested to participate, please do not hesitate. It's really open to anyone, so you can follow what happens and get. We also publish a sort of a chronicle where we have just some news to share with the people. And thank you. I'm open to question time.
Thank you very much for this enlightening talk. I think there are probably many questions for you because that's so gross. So want to start? Somebody? Right?
Yes, thank you very much. Really impressive. This sounds fantastic. One baseline question: are there any contenders to this project for 2040? What would be the other what are the other big projects proposed that this is a wide-field spectroscopic telescope must compete against?
Yeah. So this is my next slide. So today, as I know, because the one which are on the market, I would say, it's the Atlas, which is there for some time. It's a 50-meter single dish millimeter antenna. Mm-hmm. There is the ALMA 2040, which is an upgrade of ALMA. I don't think they have decided that if they want to extend more baseline and so on. There is a kilometer VLTI, which is a kilometer baseline interferometer. Basically, the idea is to have another UT, but at a kilometer and increase the VLTI baseline. And there is a TDT, which is a set of many small telescopes to perform time domain science. So this is what I know.
Thank you. Very, very interesting and promising. Actually, my question was the one that I did, but I had another one, a little bit more technical. Perhaps it's too soon to say anything about this, but could you comment on the target selection for the most survey? Because you're going really deep, so I guess you will need to based on photometry from SST or something like this.
Yeah. So in fact, yeah. So for catalog, I think SST will provide most of it. We have also Euclid and so on. So and on the stellar, we have Gaia. So I don't think we will be in trouble to do our own imaging to get the target selection. So I think the thing is how to efficiently do that with multiple surveys. So we will start soon to experiment that with 4 modes, which is our multi-survey at the time. We know it's not easy. And then if you include time domains, it's even more difficult. But the good thing is that we have 30,500, which is a huge number. In many cases, you don't need all of them. Cosmology probably will want all of them, but in some cases, for example, time domain, mostly was expected is 1,000 events to look at. So it will be easy, let's say, to allocate 20,000 of them. So in many cases, for the various science cases, we are going to do the exercise. We see that a sort of unique survey can merge multiple surveys. Then the FS, and the FS goes well into it, usually, because most of the objects you're looking at, there's a central object connected to something else. So I think, in a way, this is a sort of multi-scale thing we want to do. So I think we are doing this exercise. It's part of what we plan to do, and we plan to in our answer to result that in operation scheme, yeah, we know how to do it, or at least start to know. It will have to be developed over time, of course. But I think we are in good shape. So we are doing a survey plan with a few of the surveys that we are already identified to see how we can effectively put all them together. So we have a survey simulator, the ETC, and so on to do that. And so that's, I think, it's a very interesting exercise. It's an exercise as well.
Sorry.
Yeah, excuse me. You've cited the case of the Sloan digital space survey as a strong success. I think that most of the reason to be such a successful proposal was because of the data, but policy to make everything public.
Yeah.
Do you have something similar, or what is the philosophy you're going to have?
Yeah.
To make?
So at the end will be decision from ISO, which is the community, to do that. So what we foreseen, yes, it follows the same scheme to make it public. I think we cannot see that such a policy will not make public the data, of course. Then we have to make what time scale you do release and so on. Of course, we want to do much more. So we will publish really reduce data, but also advanced data products. And this is where you have to work. For the most, I think it's already challenging, given the number of things. For the FS, it's even more, because you don't know, you have to find a way to detect automatically objects, classify them, and so on. But this it's something that we plan to do. And this is where we hope the community can help to develop the tool.
Yeah, one of the big success you mentioned was from Muse and other instruments, but in particular for Muse and the relation with the question by someone is to provide this added value data products, and in particular good calibrated data for the community, public and so on. That will be, you mentioned before, the number of archive papers that are being published just with Muse is amazing. So the data are there, but they're well prepared to be used.
Yeah.
So this is a nice thing that the community would enjoy a lot to for produce science. I have another question in relation to many, but just to you mentioned that would be one of the facilities that it's a facility itself. It's not just an instrument, it's more than that. But that you are multifocal observation simultaneously. That can you elaborate a bit more? This is interesting. Or
Yeah. So if you go to the right, so yes, so this one. Right. Yeah, so sorry. Off.
yeah.
Yeah, so yeah, so optically you just extract, so you in the field of view. No, that was it's I want to see where it is. Oh, sorry. Yes. So in terms of the field of view, so the field of view, the central field of view is lost, but it's only 39 meters at 2 degrees for the mass. It's lost, but there will be signs. Only maybe a small things that will have not seen because there is some difference between the two. But it will have, of course, all the FS performing. So in fact, same wavelength range and so on. So how we do that? So optically, we have a system that can extract the light and put it at the right focal plane and so on. How then we have to see what system will guide the telescope and how this is transferred. So it's all of a question of the control system, wavefront sensing, and so on. Doesn't seem to be extremely difficult, to be tight, and so we have to be sure, but it's not something major. And in the FS trend, which has a lot of mirrors, there is a place to put a GLO mirror to do adaptive optics then.
Because of different
Yeah.
field of view.
So all the idea is to maintain, and then the system are completely independent in a way. Okay, so that provides some constraint. You cannot do calibration that will provide bad light to the FS and vice versa. Okay, but if you foresee from the start, this is really feasible. Okay, it's almost impossible to implement afterwards, but from the start, yes. And then, so typically, you do an observation. So you are in a position on the sky as dictated by the MOS or by the FS. But the MOS has always to do, because we go deep, so always to do, let's say, multiple configuration to cope with the clustering of the source. So we spend some time. So you do an exposure, then move the fiber, and this will be done with the telescope fixed. And at the same time, completely independently, you do an exposure, the 3/5 minute with the FS, and either you move it, and you do a big mosaic, or you do deeper on one field, so you can do what you want, or you can even follow a moving object.
Any more questions? I have another one, but it will be the last. Okay, sorry.
It's a more generic question. So we know with the current telescopes and stuff, what problems we have been able to solve and what we are not able to solve. So with WST, what 3 problems you would think of that are more likely to solve with this facility that we are not able to solve right now?
Yeah. But the problem I think we are going to solve is not the one that we're going to encounter. The one difficult to solve, by definition, the one that we are not foreseen. Anyway, yeah. So what are the challenges? Yes, anyway, so that I will translate your question in that way. So I think telescope, there is this multiple focal plane at the same time, but I will see it as relatively easy, certainly much easier than the ELT. We use part of the technology of the ELT. So I think there's a few challenges. The coating should be extremely efficient for the FS given our train. So we need to work on that. We are working on them. Okay. The instrument. The instrument by each individual instrument is something we know how to do. It's just that we are not doing 2 spectrograph, we are not, or even 24 like we do. We do 300. Mean that we need to move to small series or even series scale with industry. So ISO has done that with the AT to produce all these segments. Doing that with spectrograph, which are complicated and more complex than just a segment, is maybe a challenge that we have to develop and so on. So we have to work closely with industry. And in a way, what will be the different role of ISO, the consortium, and the industry will probably be different with what we're doing now. We are not going probably to do that as we are doing with the IT instrumentation, for example, which are huge. Like here, the instrument, more or less, the instrument will be 2/3 of the cost of the facility. So it will be the major challenge in terms of industrialization. And then the operation is the next challenge. Operation is mostly we'll have here the community to work hard with ESO to make it happen.
More questions? Roland will be here today and tomorrow morning. And he's in my office, so you can reach him and ask questions or anything. He's very willing to meet the, in particular, all the generation, but in particular the youngest one.
Maybe the old one as well.
Because of the nature of the project, but also thank you for coming for putting Spain in the, for changing the color of Spain in this project, in this amazing project, and when we maybe we can have some tapas now too.
Okay, thank you very much.